Hello everyone, welcome to my YouTube channel Physics for Everyone. So today we are going to discuss about time dilation. So in upcoming videos I will be discussing some of the basic concepts of physics and mathematics. You can also suggest me as well which videos you want to see, and if you have any doubts you can ask me in the comment box below. So coming to the video, time dilation. So before going into this topic, let me brief you some history regarding this time dilation. Long back in 17th century, Sir Isaac Newton proposed classical physics in a very good manner, and he proposed that time is absolute everywhere in this universe. That means if you are on Earth, or if you are on Saturn, or if you are on any other planet in other galaxy, the passage of time will be same for everyone. That is the absolute nature of time. But in 20th century, Albert Einstein came up with a very good mind-boggling thought experiment which led to the concept called time dilation. So time dilation means time is not absolute so far. The time for you, for me, and for any other guy who is traveling in an aircraft, the time ticks very differently for us. So how Einstein got this idea? It's a very good idea. So it depends on the speed of light. So you may be thinking how the speed of light and the time dilation is connected together. So let me give you a brief idea about this. First of all, we have to take this phrase, the constant speed of light. That means in the universe, the speed of light is constant. Even though if you are traveling with a light beam with a velocity v to an observer outside your frame of reference, the speed of light is not c plus v. It is only the light. It is only c, which means in a normal day life we'll be encountering these type of scenarios, like you are traveling in a train, and for example another train has been passed away beside you with a velocity u in opposite direction. Then you may say that the velocity of the train with respect to u will be v plus u, but that is not the case with the light beam. That means if a light beam has been passed beside you and you are traveling in a train with with a velocity v, you cannot say the speed of light is c plus v. It's always c. Then which is right and which is wrong? So there comes the concept time dilation. So you may thought that the speed of light is v plus c in the previous scenario which I said before, but it is not the case. If you measure the speed of light, it will be c. That means the speed is nothing but distance by time. Speed is nothing but distance by time. So in order to make the speed of light as constant, these two things, distance and time, has to change in order to keep it constant. Since the distance is changing because the light beam is moving, the time has to change in order to keep the constant speed of light. So that is the idea behind the time dilation. So in order to have a constant speed of light, the time has to change. So I will show you the mathematical derivation, but before going into that, let me introduce a clock because we need to measure the time dilation. So I am introducing a clock. In this clock, we are having two mirrors, and a photon, a light beam. So that photon will bounce back and forth between these two mirrors. So it will bounce between these two mirrors. Okay. So if the photon is traveling from this mirror to this mirror, then it will take 1 second. Let us suppose, because if that is the case, the distance between these two mirrors must be 3 lakh kilometers approximately, because the speed of light is 3 lakh kilometers per second. But let us suppose the time taken by the photon to start from this mirror to reach this mirror is 1 second. So this is the clock. We are having two mirrors. The photon is moving between these two mirrors. So this is the clock. So by using this clock, now I am deriving the time dilation equation. Let us suppose this is the stationary clock, and this is one scenario, and in another scenario this clock is moving with a velocity v in this direction. Then what happens, if you see, when the photon starts from this mirror, it no longer sees the mirror right above this mirror, because this mirror is moving in this direction with velocity v. So it will see the mirror at this point. So instead of traveling a distance of L, as I said before here, it will travel a distance of L dash. Yes? Okay. So let us suppose in stationary clock, the time taken by the photon to travel from this mirror to that mirror is delta Ts. The subscript S is for stationary clock. And here, when the light beam travels from this mirror to this mirror, it takes time Tm, delta Tm. M is for moving clock. Okay. So I can use some of the basic mathematics here. The distance taken by the mirror from this point to this point is nothing but v into delta Tm, because it is traveling in this direction with v, and the time taken by the uh, light beam from here to here is nothing but Tm, and which is nothing but our clock Tm. Okay. And this distance is nothing but c into delta Ts, which is nothing but the time that will take by the photon in a stationary clock to move from this point to this point. That is c delta Ts. So as I said before, I want to measure the time taken by the stationary clock and the time taken by a moving clock. So now I will find the ratio between the moving clock time and the stationary clock time. So before going into that, so I'm here, I'm having a simple derivation. You can see L is nothing but C delta Ts, as I said before. L is nothing but the time taken by the photon in stationary clock, and L dash is nothing but the distance traveled by the, sorry, yeah. So L dash is nothing but the distance covered by the photon in moving clock. So that I can write as L dash square by using Pythagoras theorem. L dash square of the hypotenuse is nothing but sum of the squares of the sides. So L dash is nothing but V square delta Tm square plus C square delta Ts square. So after some manipulations, I can say L dash is nothing but C delta Ts into root of V square delta Tm square by C square delta Ts square plus 1. So finally, I would like to calculate the ratio of time taken by the moving clock to the time taken by the stationary clock, that is delta Tm by delta Ts. So which is nothing but, since the speed of light is constant, so delta T is only dependent on the length taken by the light beam. So delta Tm by delta Ts is nothing but L dash by L, because the time taken by the light beam is nothing but distance traveled by the speed of the light, right? And speed of light is constant, so it is nothing but the ratios of length taken by the photon beam. So L dash is nothing but this quantity upon L is nothing but C delta Ts. So I'm getting this one, and after some multiplications, so finally we got delta Tm by delta Ts is nothing but 1 by square root of 1 minus v square by c square. And in special theory of relativity, we call this factor as gamma. And if you see, delta Tm is some factor, that is the gamma times delta Ts, and this factor is always greater than 1 because v is always less than c. Any object in this universe cannot travel with a speed greater than c. I will tell you in the upcoming videos why it's so. So v is less than c. That means this factor is always this factor is always less than 1 because v by c is less than 1 and this factor is less than 1, and so this factor will be always greater than 1. That means the time taken by the moving clock is always greater than the time taken by the stationary clock. That means moving clocks moving clocks always slower than the stationary clocks. If it is 1 second for a stationary clock, then to make that 1 second, it will take more than 1 second, right? That means if the stationary clock is ticking 10 seconds, moving clock will move in a slow. The passage of time in moving clock is in a slow manner. So I will show you one more animation. Yeah, let us suppose we are having two clocks here. One clock is carrying by Jack and one clock is carrying by Zill. So if you see, since both clocks are stationary, here they are ticking in same fashion. It took 8 seconds to complete one oscillation between the two mirrors. Now what happens if the clock of the Zill is moving in a direction with some velocity? Say I can put it to say zero point 0.3 of c. Okay, let us say the velocity of the Zill clock is 0.3. Now see what happens. Since the Zill clock will move, the time taken by the Zill clock is the time runs slower to the Zill clock. Okay, you can see here. So as I said before, the path taken by the moving clock is more compared to the path taken by the stationary clock. So if you see, Jack clock ticks 8.37 seconds, but the Zill clock ticks only 8 seconds. That means the clock of the Zill has been slowed down because of its motion. So if you see, if I increase this to, for example, 0.6 c, and I see, it's a very good animation I found in internet. You can also have it if you want. So if you see here, Jack's clock is faster and Jill's clock is slower. And how much amount is it slower? As I said before, gamma times. If your V is increasing, for example, if you see here, if your velocity is equal to c, it's an abnormal case, but let us see what happens. If v equal to c, then gamma is 0. Sorry, gamma is infinite. I'm sorry. If v equal to c, gamma is infinite. That means the time taken by the moving clock delays infinitely. So I will show you the same thing here. So v is nothing but c. So let's see what happens. See, that means if the clock is moving with velocity of light, it will not take even 1 second. The time stops. So this is the basic idea behind black holes. In black holes, there was a theory like the time stops. This is the theory behind it. That means even though there is no motion associated with the clocks in the black hole, but the gravity itself will influence the time. That is the concept behind the general theory of relativity. I will come up to in next videos also. So this is the basic idea behind the time dilation. So I can say time runs differently for different persons, and time slows down when you are moving. But since we are moving with normally of 60 or 80, 100 kilometer per hour in daily life, you cannot see much difference in the time between you and any other guy in stationary frame of reference. But if you are moving with velocities comparable to the speed of light, then you will surely see the difference in time. That means if you are moving with zero point 0.6, zero point 0.7, zero point 0.8 c, your time runs slower compared to the one who is stationary. That means the one who is stationary will age faster than you. So this is nothing but time travel to the future. So I'm concluding this video by saying this: the time dilation is due to the motion in space. If you assume the space in x-axis and the time in y-axis, okay, then if you're if you draw a y equal to x line, then if you are moving in space, then there will be delay in the time. If you are moving in space, then there will always be a delay in time. If you plot the points on this y equal to x, this is a graphical representation, I can tell you. Okay, so whenever there is a motion in space, always there will be a dilation in time. And as I said before, if you are moving into a high gravitational potential, then also your time will delay. That I will come up in next videos. You can see that. Thank you.